welcome to this problem walkthrough. Today, we're diving into LeetCode problem number 1224, titled Maximum Equal Frequency. In this problem, we'll explore an intriguing algorithmic challenge involving arrays and frequency counts. Let's get started by understanding the problem and brainstorming approaches. In this problem, you're tasked with finding the maximum value of max frequency, which represents the largest index k such that the first k elements of an array can be rearranged to meet one of two specific conditions. First, all elements must appear the same number of times. Alternatively, all elements except one must appear the same number of times, with that one element appearing either one more or one less time than the others. The input is an array nums of positive integers, and the output is the maximum possible value of max frequency. For example, if nums has a length of 10, you determine the longest prefix of the array that can satisfy one of these conditions and return its length. The constraints require that the solution be efficient enough to handle arrays of up to 100,000 elements where each value can range from 1 to 100,000. In the first example, the input array is 2, 2, 1, 1, 5, 3, 3, 5. The output is 7, and here's why. If we take the first 7 elements, 2, 2, 1, 1, 5, 3, 3, they can be rearranged to 1, 1, 2, 2, 3, 3, 5. When rearranged like this, all the elements occur exactly 2 times, satisfying the condition where all elements have the same frequency. However, if we include the 8th element, 5, it becomes impossible to satisfy the conditions. Therefore, the maximum value of max frequency for this input is 7. This shows how we determine the longest prefix that meets the problem's requirements. In the second example, the input array is 1, 1, 1, 2, 2, 2, 3, 3, 3, 4. The output here is 10. This is because the entire array satisfies the condition where all elements appear the same number of times. Specifically, the numbers 1, 2, 3, and 4 each occur exactly 3 times in this case. Since all elements meet the criteria, the maximum value of max frequency is the length of the array, which is 10. This example demonstrates how the entire array can sometimes form a valid prefix. In the third example, the input array is 1, 1, 1, 2, 2, 2. The output is 6. Here, all 6 elements satisfy the condition where each number appears the same number of times, which is 3 occurrences for both 1 and 2. Because the entire array forms a valid prefix that meets the criteria, the maximum value of max frequency is 6. Additionally, the problem's constraints remind us of edge cases to consider, such as arrays with only one element, arrays where all elements are identical, and large arrays with diverse values. Each of these scenarios must be handled efficiently, ensuring the solution works for all valid inputs. To tackle this problem, we first consider the brute force approach. The intuition here is to test every possible prefix of the array, starting from index 0 up to index k1, for all possible values of k. For each prefix, we calculate the frequency of every number and then check whether these frequencies satisfy one of the 2 required conditions. The first condition is that all numbers in the prefix have the same frequency. The second condition is that all numbers except 1 share the same frequency, while the exceptional number either occurs exactly once more or once less than the others. However, this method has significant drawbacks. While straightforward to understand, the time complexity is quadratic, or O(n) squared, since calculating frequencies for each prefix requires O(n), and there are n prefixes to evaluate. Additionally, it does not take advantage of the fact that frequencies can be updated incrementally as we extend the prefix. As a result, this approach is highly inefficient for large inputs, making it impractical for scenarios where scalability is important. A more efficient solution builds on the insight that we can maintain frequency counts dynamically as we iterate through the array. In this optimized approach, we use 2 hash maps. The first, frequency, keeps track of how many times each number appears in the array. The second, frequency count, monitors how many numbers occur at each frequency level. With these 2 data structures, we can update frequency information incrementally for each new array element. At every step, we verify if the current frequency distribution satisfies one of the problem's conditions. Specifically, we check if all numbers share the same frequency, or if all but one number share the same frequency, with the exceptional number deviating by exactly 1 or occurring only once. The beauty of this method lies in its efficiency. By analyzing the size of frequency count and the specific values it contains, we can determine in constant time whether the conditions are met for the current prefix. This eliminates the need for recalculating frequencies from scratch at each step, making the approach highly efficient. The implementation of the optimized approach involves three main steps. First, we traverse the array while updating the frequency and frequency count hash maps. These updates ensure that as we process each element, we maintain an accurate record of frequencies and their occurrences. Second, at each step, we evaluate whether the current prefix satisfies the required conditions by analyzing the frequency count structure. Finally, we keep track of the maximum index k where these conditions hold true. In terms of complexity, this method processes each element in constant time, leading to an overall time complexity of O(n). The space complexity is also O(n), as the hash maps grow with the number of unique elements in the array. This strategy is both efficient and scalable, leveraging the incremental nature of the problem to avoid redundant computations and enabling it to handle large inputs effectively. The key insight that makes the optimized approach so powerful is the realization that frequencies and their counts can be tracked incrementally. Instead of recalculating everything for each prefix, we simply update the frequency and frequency count maps as we process new elements. This eliminates redundant work and allows us to check the conditions for each prefix in constant time. When comparing the two strategies, the brute force method is simpler to understand and implement but suffers from a prohibitive O(n)² time complexity, making it impractical for larger arrays. The optimized approach, on the other hand, is slightly more complex to implement but achieves a much better O(n) time complexity, making it the superior choice. By carefully managing hash maps to track frequencies and their occurrences, this approach ensures efficiency, scalability, and correctness, making it the clear strategy to adopt for solving this problem. To fully grasp the solution, we first need to clarify the problem's requirements. The goal is to examine an array called nums and identify the longest prefix, which is a subarray starting from the first element, that satisfies specific frequency-based conditions. For instance, we might need to ensure that all the elements in the prefix occur with the same frequency, or perhaps allow one element's frequency to differ by at most one. These conditions define what makes a prefix valid, and our task is to determine the maximum length of such a prefix. The first step is to outline the constraints and inputs. We're given an array nums of size n, and from this, we need to check prefixes incrementally. The conditions can vary, but a couple of examples could include requiring uniform frequencies across the prefix or allowing a small deviation in the frequency for one element. By formalizing this, we give ourselves a clear framework to build the solution upon. One way to approach this problem is through a brute force method. Here, we check each possible prefix of the array to determine which is the longest one meeting the conditions. To do this, we iterate through all potential prefix lengths, from 1 to n. For each prefix, we calculate the frequency of each element using a frequency map, which is essentially a dictionary where keys represent elements and values represent their counts. Once the frequency map is built for a prefix, we validate it against the required conditions. If the conditions are satisfied, we update the maximum valid prefix length. While this method is straightforward, it involves recalculating frequencies for every prefix and performing validations repeatedly, leading to inefficiency. To address this, we can adopt an optimized approach using a sliding window. Here, we maintain a frequency map dynamically as we expand the prefix one element at a time. After adding a new element to the prefix, we validate the frequency map. If the conditions are violated, we adjust the prefix by removing elements from the start, effectively sliding the window forward. This approach ensures we only process each element once, significantly improving efficiency while still tracking the longest valid prefix. To optimize further, there are a few key insights we can leverage. First, the frequency map is central to the solution. It helps us track the count of each element in the current prefix, enabling quick validation of the conditions. Instead of recalculating the entire map for every prefix, we perform incremental updates by adding or removing one element at a time. This reduces redundant computations. For the conditions, we check two possible scenarios. In condition A, all values in the frequency map must be equal. In condition B, we allow at most one frequency value to differ by 1. These validations ensure the prefix remains valid. The sliding window approach is particularly efficient because, as we adjust the prefix dynamically, we avoid the need for recalculating frequencies from scratch. This reduces the time complexity of the solution from O(n) squared in the brute force approach to O(n), making it scalable for larger arrays. To implement this solution effectively, we rely on specific data structures. The frequency map, which is implemented as a dictionary, is crucial for tracking how often each element appears. For example, a map like 1, 2, 2, 3 indicates that the number 1 appears twice and the number 2 appears 3 times. Dictionaries are highly efficient for this purpose, offering average O(1) time complexity for insertions and lookups. Additionally, we can maintain a maximum frequency tracker to quickly validate condition B, where we allow one frequency to differ by 1. This optional optimization can simplify certain checks. Beyond the data structures, we also need to account for edge cases. If the array is empty, there's no valid prefix, so we return 0. For an array with a single element, any prefix is valid, as the conditions are trivially satisfied. Similarly, if all elements in the array are identical, the entire array forms the longest valid prefix. Lastly, we must handle cases where no prefix satisfies the conditions, in which case we also return 0. By considering these structures and edge cases, we ensure our solution is both robust and efficient. Finally, let's analyze the complexity of our approach. The sliding window technique ensures that each element in the array is processed only once. With the frequency map allowing O(1) average time complexity for updates, the overall time complexity of the solution is O(n). This is a significant improvement over the brute force method, which required O(n squared) operations. For space complexity, the frequency map requires storage proportional to the number of unique elements in the array, denoted as U. Thus, the space complexity is OU. This makes our solution not only fast but also space efficient, as the size of the frequency map is typically much smaller than the size of the array. By balancing time and space efficiency, the sliding window approach provides an optimal solution to the problem. Here, we begin by importing the counter class from the collections module, which will help us efficiently manage frequency counts. Inside the solution class, the method max_frequency is defined. This method takes a list of integers, nums, and aims to determine the maximum prefix length where the frequency of elements satisfies certain conditions. To achieve this, two counter objects are initialized: frequency, which keeps track of the frequency of each number in nums, and count, which monitors how many numbers share a particular frequency. We also initialize max_length to 0, which will store the result. The for loop iterates through nums, using both the index I and the value number. For each number, if it already exists in the frequency counter, we reduce the count of its current frequency in the count counter. If this adjustment causes the count of that frequency to drop to 0, we remove it from count to keep the data clean. Next, we increase the frequency of number in frequency and update count to reflect this change. With these updates, we then check if the prefix up to the current index meets our condition. If count has only one key, it means all numbers in the prefix share the same frequency. In this scenario, we check two cases: either the frequency is 1, or there's only one number with this frequency. If either is true, we update max_length to include the current prefix length. Additionally, if count has two keys, it indicates two types of frequencies are present, and we will handle that condition next. Now, when we encounter two distinct frequencies in count, we sort the keys to analyze them. If the smaller frequency is 1 and only one number has this frequency, it means we can form a valid prefix by removing the single element with frequency 1. In this case, we update max_length to include the current prefix length. Alternatively, if the larger frequency is exactly one more than the smaller frequency and only one number has this larger frequency, it implies that we can form a valid prefix by reducing the count of the number with the higher frequency. Again, we adjust max_length accordingly. Finally, once the loop completes, we return max_length as the result. This represents the length of the longest prefix where the frequency of elements satisfies the given conditions. The algorithm efficiently ensures that we account for all possible valid prefixes while maintaining optimal performance through the use of the counter data structure. Here, we start by defining a Java method named maxEqualFrequency that takes an array of integers, nums, as input. To solve the problem, we use two hash maps. The first map, frequency, keeps track of the frequency of each number in the array, while the second map, count, tracks how many numbers have a specific frequency. Additionally, we initialize maxLength to 0, which will store the maximum length of the prefix that meets the required condition. Now, we iterate through the array using a for loop. For each number in the array, we first check if it already exists in the frequency map. If it does, we reduce the count of its current frequency in the count map. If the count of that frequency becomes 0, we remove it from the count map to keep it clean. Next, we increment the frequency of the current number in the frequency map and update the count map accordingly. Finally, we check if the current prefix satisfies the condition by examining the size of the count map. If there's only one unique frequency, we prepare to handle that case. In this part of the implementation, we handle the scenarios where the size of the count map is either 1 or 2. First, if there is only one unique frequency in the count map, we retrieve its key. If that frequency is 1, or if there is only one number with that frequency, we update maxLength to include the current index plus 1, indicating the entire prefix up to this point meets the condition. Next, if there are two unique frequencies, we convert the keys of the count map into a list and sort them. This allows us to check specific conditions. If the smaller frequency is 1 and only one number has that frequency, we update maxLength to include the entire prefix. Alternatively, if the difference between the two frequencies is exactly 1, and only one number has the higher frequency, we also update maxLength. These checks ensure that the prefix meets the required conditions in all scenarios, and at the end of the loop, we return the maximum valid prefix length stored in maxLength. Here, we are starting with an example where nums is 1, 2, 3, 4, 5. Initially, both the frequency map, frequency, and the count map, count, are empty, and the maximum length, max_length, is set to 0. Now, for the first number, 1, we increment its frequency in the frequency map, so frequency becomes 1, 1. Then, we update the count map to reflect that there's now one number with a frequency of 1, making count equal to 1, 1. Since there's only one frequency present, we update max_length to 1. Next, for the second number, 2, we increment its frequency in the frequency map, so frequency becomes 1, 1, 2, 1. The count map is updated to show that there are now two numbers with a frequency of 1, resulting in count being 1, 2. Again, all elements have the same frequency of 1, so max_length is updated to 2. For the third number, 3, we increment its frequency in the frequency map, so frequency becomes 1, 1, 2, 1, 3, 1. We then update the count map, which now shows three numbers with a frequency of 1, making count equal to 1, 3. Since all elements still share the same frequency, max_length is updated to 3. Similarly, for the fourth number, 4, its frequency is incremented in the frequency map, resulting in frequency equals 1, 1, 2, 1, 3, 1, 4, 1, and the count map updates to 1, 4. With all numbers still having the same frequency of 1, max_length becomes 4. Finally, for the fifth number, 5, we increment its frequency in the frequency map, so frequency becomes 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and count updates to 1, 5. Again, all numbers share the same frequency, so max_length is updated to 5. The final output for this example is max_length equals 5. Now, let's consider another example where nums is 1, 1, 2, 2, 3, 3, 3. Initially, frequency and count are empty, and max_length is set to 0. For the first number, 1, we increment its frequency in the frequency map, making frequency equals 1, 1. The count map updates to 1, 1, reflecting one number with a frequency of 1. Since there's only one frequency present, max_length becomes 1. For the second occurrence of 1, we first decrement its previous frequency in the count map, reducing count 1 to 0 and removing it. Then, we increment the frequency of 1 in the frequency map, making frequency equals 1, 2, and update count to 2, 1, indicating one number with a frequency of 2. Since there's still only one frequency present, max_length becomes 2. For the third number, 2, its frequency is increment in the frequency map, so frequency becomes 1, 2, 2, 1. The count map is updated to 2, 1, 1, 1, reflecting that there's one number with a frequency of 2 and one with a frequency of 1. In this case, two frequencies exist, 1, 2, but the condition holds because there's only one number with a frequency of 1. Thus, max_length is updated to 3. For the next occurrence of 2, we first decrement count 1 to 0 and remove it. Then, we increment the frequency of 2 in the frequent map, resulting in frequency equals 1, 2, 2, 2, and update the count map to 2, 2. Since all elements now share the same frequency, max_length becomes 4. For the fifth number, 3, its frequency is increment in frequency, so frequency becomes 1, 2, 2, 2, 3, 1, and count updates to 2, 2, 1, 1. Again, two frequencies exist, 1, 2, but the condition holds because there's only one number with frequency 1. Thus, max_length is updated to 5. Now, for the sixth number, 3, we first decrement count 1 to 0 and remove it. Then, we increment the frequency of 3 in the frequency map, making frequency equals 1, 2, 2, 2, 3, 2, and update count to 2, 3, indicating all elements now share the same frequency of 2. Therefore, max_length becomes 6. For the seventh occurrence of 3, we first decrement count 2 to 2. Then, we increment the frequency of 3 in frequency, so frequency becomes 1, 2, 2, 2, 3, 3, and count updates to 2, 2, 3, 1. Here, two frequencies exist, 2, 3, and the condition holds because there's only one number with the higher frequency of 3. Thus, max_length is updated to 7. The final output for this example is max_length equals 7. In this example, nums is 10, 10, 10, 10, 10, 10, 10. Initially, frequency and count are empty, and max_length is set to 0. For the first number, 10, we increment its frequency in the frequency map, resulting in frequency equals 10, 1, and update count to 1, 1, indicating one number with a frequency of 1. Since there's only one frequency present, max_length becomes 1. For each subsequent occurrence of 10, from the second to the seventh, we increment its frequency and update the count map accordingly. At each step, all elements share the same frequency, so max_length is updated to the current step. By the end of the array, frequency becomes 10, 7, and count equals 7, 1, and max_length reaches 7. The final output for this example is max_length equals 7. To analyze the time complexity of the solution, we break it down step by step. First, initializing the frequency and count dictionaries as counter objects is an O1 operation. Next, the main loop iterates through the nums array, and if the size of nums is n, this contributes O(n) to the overall complexity. Within this loop, for each number in nums, its frequency is updated in O1 time, as modifying a dictionary entry is a constant time operation. Similarly, updating the count dictionary, which tracks the number of elements at each frequency, also involves constant time operations like incrementing or removing a frequency. Finally, the solution checks whether the current state of frequencies satisfies the problem's constraints. Since the count dictionary contains at most two distinct frequencies at any time, evaluating these conditions is also an O1 operation. Each of these steps contributes to the overall efficiency of the algorithm. Now, combining all these operations, we see that for each of the n elements in the array, all updates and checks within the loop are performed in O1 time. As a result, the total time complexity of the solution is O(n). Shifting to space complexity, the frequency dictionary stores the frequency of each distinct number in the array. In the worst case, if all numbers in nums are unique, the size of frequency will be O(n). The count dictionary, on the other hand, tracks the counts of those frequencies and can only ever contain at most two distinct entries, making its size O(1). Additionally, a few auxiliary variables like I, number, and max_length are used, which require O(1) space. Therefore, the overall space complexity is determined by the frequency dictionary and remains O(n). To highlight the efficiency of this solution, it's useful to compare it with a brute force approach. A naive method might involve recalculating the frequency of each number and validating the conditions for every prefix of the array. For a prefix of length I, recalculating frequencies would take I time, and summing this over all prefixes results in an n squared time complexity. In contrast, the optimized solution avoids recalculations by maintaining frequency counts incrementally, reducing the complexity to n. This improvement is mathematically justified since all updates and checks within the loop operate in one time, and the loop runs for n iterations, leading to an overall complexity of n. Considering best, average, and worst cases, the time complexity remains n for all scenarios, whether the elements are all the same, randomly distributed, or entirely distinct. Similarly, the space complexity is dictated by the number of unique elements in the input, which also results in n usage in the worst case. This consistent efficiency across all cases underscores the robustness of the solution. When solving problems like maximum equal frequency, there are several common mistakes to watch out for. One of the most frequent issues is overlooking edge cases. For instance, scenarios with empty arrays, single-element arrays, or inputs at the boundaries of the constraints can often lead to runtime errors or incorrect outputs if not handled explicitly. Testing these boundary conditions is critical to ensure your solution is robust. Another mistake is relying on an inefficient brute force implementation. For example, iterating over all subarrays without optimization can easily result in time limit exceeded errors, particularly for large input sizes. This highlights the importance of analyzing time complexity and avoiding approaches with n cubed or similar inefficiencies. Additionally, problems involving sums or products often trip people up if they overlook the impact of negative numbers. For example, when working with maximum product subarrays, it's essential to track both maximum and minimum values to handle negatives correctly. Finally, when using techniques like sliding windows, errors in updating pointers or maintaining the state of the window, such as sums or counts, can cause incorrect results or even infinite loops. Careful debugging and validation are key to avoiding these pitfalls. Misinterpreting problem constraints is another area where mistakes commonly occur. For example, if the problem specifies that the array is sorted or requires unique solutions, misunderstanding these details can lead to unnecessary complexity or faulty logic. Always ensure you fully understand the constraints before designing your solution. Now, when it comes to interviews, there are a few key strategies to keep in mind. First, focus on pattern recognition. Many array problems share underlying patterns, such as sliding windows, prefix sums, or binary search. Being able to quickly identify which technique applies to a given problem is a valuable skill. Also, interviewers often appreciate discussions of trade-offs. While brute force solutions may not be optimal, they can help you build toward a better approach incrementally, and clear communication of your thought process matters. Additionally, make a point to highlight potential edge cases as you explain your solution. This demonstrates your thoroughness and deep understanding of the problem. Finally, be prepared to discuss space versus time optimization. Sometimes, an n time solution might use extra space, while a more space-efficient approach could be slower. Being able to evaluate and articulate these trade-offs is a valuable skill in interviews. To further strengthen your understanding, it's helpful to explore related problems that share similar concepts or techniques. For instance, LeetCode 53, Maximum Subarray, focuses on finding the maximum sum of a contiguous subarray, and it's solved efficiently using Cadon's algorithm. Another example is LeetCode 209, Minimum Size Subarray Sum, which uses the sliding window technique to find the smallest subarray with a sum greater than or equal to a target value. LeetCode 560, Subarray Sum equals k, introduces the use of prefix sums combined with a hash map to efficiently compute subarray sums. This approach is particularly powerful for problems that require frequent sum calculations. Lastly, LeetCode 152, Maximum Product Subarray, emphasizes tracking both maximum and minimum products to account for the effect of negative numbers, a detail that is often overlooked. Practicing these problems will help you recognize patterns and refine your approach to similar challenges. When thinking about alternative approaches and their trade-offs, it's important to consider the specific requirements of the problem. The sliding window technique is an excellent choice for problems involving contiguous subarrays where quick updates are needed. However, its trade-off lies in the careful pointer management it requires, as even small mistakes can lead to incorrect results. On the other hand, prefix sums are highly effective for problems involving subarray sums or differences. This method simplifies some calculations to O1, but it does come with the cost of additional space for storing the prefix array. Another powerful technique is using a hash map for optimization. This is particularly useful for problems that require tracking sums, products, or frequency counts efficiently. While this approach significantly reduces time complexity for queries, it does increase space complexity due to the storage requirements of the hash map. Understanding these trade-offs allows you to choose the best approach based on the problem's constraints and priorities. Great job making it to the end of this problem. To recap, we tackled the maximum equal frequency challenge by leveraging hash maps for efficient count tracking. This problem highlights the importance of understanding frequency conditions and using the right data structures. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!